Hello? Hello? Hello?
Hello.
How's it going?
Good.
Right now I'm just waiting to see who else is going to be joining in. How's your summer ending?
Few weeks left.
I'm sorry?
Not in yet. Like still a few weeks left.
Okay. So what do you have for the next few weeks before school starts?
I'm gonna take SAT test.
Okay, which test are you going to take?
SAT.
SAT, okay. Have you taken it before?
Yeah.
Okay. Yeah, I am not a huge fan of the standardized tests. It gets worse when you are applying for graduate school and you essentially have to take the SAT all over again.
Yeah.
It looks like we have 2 people online now. Excellent. Everybody's online. Terrific. All right. Can everybody see my screen? And is it, slide 1 from zombies to Fibonacci's?
Yes. Yes.
Okay, excellent. So what I want to do today is I want to hopefully have this as the last of our group lectures so that we will now be at the point where we can start doing a research problem. So the goal is to get you to do something new. Now, math research can be extremely rewarding, but it can also be very frustrating. It can take a long time to make progress. Fortunately, there's 3 of you. And so you can communicate amongst each other. The other thing is I have a couple of undergraduates who have worked on related problems with me. And I'm happy to have them available to you as TAs so that you can talk to them. The only thing is the purpose of the undergraduates is more to help make sure you understand what's been done or to help you with some of the background material. It's not for them to prove the results. The goal is for you to prove the results. Okay?
Okay.
But if you are interested, I can definitely have students made available. And I have students who are both, American students, as well as students who have come from mainland China who are now studying in America. So you can think a little bit about who would you like to talk to. They also become excellent resources when you're trying to consider, if you want to come to an American school for college, which school might be a good one for you and how to help navigate the process. Okay, so what I want to do today is I want to focus really on just the material that we need for the new problem. So in lecture 3, I went over a couple of games. I went over, first of all, not really a game, but just a geometric way to prove that the square root of 2 is irrational and some generalizations. And the purpose of that was to show that you can do original new good work without having calculus, without having a lot of mathematical material. But the challenge is you have to be very creative. And it can take a long time to see the right way to look at problems. And so as you're going through everything, it could take a while to figure out how can we approach things. Then we went through a couple of games. We went through the tic-tac-toe game, and the big takeaway from that was trying to figure out how can we analyze a complicated problem? How can we break it up into smaller parts that are more manageable? We then went from there to the rectangle game, and then after that was the zombie game, and then after that was, I think, the triangle game. Now, in the zombie game, the big idea was a monovariant. So a monovariant is a concept that's usually not discussed in high school. It's sadly frequently not discussed in college either. most quantities in life go up and down. A monovariant is a quantity that only moves in one direction. And it turns out that if you can find a monovariant, it's often a tremendous tool for analyzing a problem. The difficulty is finding a monovariant for the problem. In some sense, the monovariant is more like art than mathematics, or if you want, and you think that math and art can together, you need to be creative to figure out what is the right monovariant to look at for the problem. If you are interested in monovariants and want more, let me know and I can give you some reading on other related problems. And then what we want to do is we want to go into the Zeckendorf game. So I just want to check and see what these slides is here. So this was the Isle of Rectangles. Okay. So let me just review some of the Fibonacci stuff. So we're going to define the Fibonacci's as 1, 2, 3, 5, etc. So we don't have two ones, we don't have a zero. And then we have the Zeckendorf theorem. Every positive integer can be written as the sum of one or more non-consecutive Fibonacci numbers. And we've talked about how to prove this two different ways. The first is the greedy algorithm. And so we take our number and we subtract the largest Fibonacci number less than or equal to. We look at what remains and then subtract the largest Fibonacci less than or equal to that. And so here's the decomposition for 2018. Now to get 2019 from this is very easy. I just add 1. And when I add 1, F2 plus 1 is going to just become F3, and F3 is still going to be 2 away from F5, so everything else will be unchanged. Now, it turns out that this is an equivalent definition of the Fibonacci numbers. So let's look at this as our definition of the Fibonacci's, or a definition of a sequence, and see what sequence we get. So we want a sequence of numbers such that every positive integer can be written uniquely as a sum of one or more non-consecutive terms. So we start with the number 1. We want to get the number 2. Well, we can't get 2 as a sum of non-adjacent terms of our sequence because the only number we have is 1. So we have to add 2 to our sequence. Now we only have two numbers, 1 and 2. We can't add them because they would be consecutive, so we have to add the number 3. Can we get the number 4 as a sum of non-consecutive terms?
Yes.
Yeah, 3 plus 1. So we don't need to add 4. Can we get 5?
No.
No, so we have to add 5. Can we get 6?
Yes. Yeah.
Yes, 5 plus 1. Can we get 7?
Yes.
Yeah, 5 plus 2. But we can't get 8. So it's a nice exercise. You should try to prove that this is equivalent to the definition of the Fibonacci numbers, that you get the same sequence. So this is a wonderful idea in mathematics. Can you come up with two equivalent definitions of the same concept? If so, sometimes one is more useful for study than another. So it's a really good homework problem. Prove that these two definitions are equivalent, that this decomposition result will give the same sequence. All right. Now, the next thing we need is this notion of sum and minimality. So what does that mean? Well, if I have a decomposition, I can ask how many terms do I have in my decomposition? So I can write 18. Its Zeckendorf decomposition is 13 plus 5. It has 2 summons. I could also write it as 13 plus 3 plus 2, which has 3 summons. And so there's a beautiful theorem that says that the Zeckendorf decomposition is sum and minimal. That means that there is no decomposition that has fewer terms. There might be a decomposition that has the same number of terms, but nothing fewer. So 8 plus 8 is 16, correct?
Yes.
How would you write 16 as a sum of Fibonacci numbers?
13 plus 3.
13 plus 3. So 13 plus 3 is the Zeckendorf decomposition, and that has two summons. 8 plus 8 also has two summons. Also, both of them are Fibonacci's. It's not a legal decomposition, but it's still a sum of Fibonacci numbers. So we can see just by looking at the number 16 that there will be times when we will have other decompositions that have as many terms as the Zeckendorf, but nothing will have fewer. So a big question becomes, for what other sequences is your legal decomposition going to be sum and minimal? And we're not going to really talk too much about that. I'm just going to leave the slide here and I'm going to go on immediately. I'm going to prove for the Fibonacci's that nothing can have fewer summons than the Zeckendorf. And the idea is to create a monovariant. So I really want to make sure we all understand the stuff here. So let's let D be some decomposition. I'm going to have some number of F1s, some number of F2s, all the way up to some number of Fn's. Where my F1 through Fn's are my Fibonacci numbers. Okay? So if I had 13 plus 3, then I would have no 1, so B1 would be 0. I would have no 2, so B2 is 0. I would have 1, 3, so B3 would be 1. I would have no 5s, so B4 would be 0. I would have no 8s, so B5 would be 0, but I would have 1, 13. And now we're going to define the index of a decomposition to be this weighted sum of the B's. It's going to be, if we have BI FI, it'll be BI times I. So it'll be B1 times 1 plus B2 times 2, all the way up to Bn times n. So what this means is the larger the Fibonacci number you have in your decomposition, the more weight it contributes to the index. Okay? Now, in the Zeckendorf decomposition, what can you tell me about the values of the B's? So for the Zeckendorf decomposition, what is true about the value of the B's? So somebody help me out. What can you tell me about the B's? All right, somebody tell me what a Zeckendorf decomposition is. What's a legal Zeckendorf decomposition?
Unique and non-consecutive.
Okay, so it's more than just unique and non-consecutive. You can't have any repeated digits. You can't have any Fibonacci summons, right?
Yeah.
So what does that imply about the B's in a Zeckendorf decomposition? So you have to convert no repeated summons and nothing adjacent to statements about the B's. What does no repeated summon mean about the B's? What can you deduce from that?
B is always 1.
Not almost. Not quite always 1. What else could the B's be?
0.
Yeah, if you say that the B's have to always be 1, then that means you have F1 plus F2 plus F3 plus F5 plus F8 plus F13. Because we can't have any repeated summons, it means each B is either 0 or 1. So you really want to be able to extract from statements consequences. Now the next thing is we can't have two adjacent terms. So what else does that tell you about the B's? So you can't have adjacent terms. What does that mean about the b's? What are your thoughts?
So if B1 is 1, then B2 has to be 0.
Good. More generally, if BI is 1, what do you know?
BI plus 1 is 0, and BI minus 1 is 0.
Excellent. So you know you can't have two consecutive b's being non-zero. Excellent. All right. So what we're going to do is imagine we have a decomposition, and I'm not assuming it's a Zeckendorf, I'm just assuming it's a decomposition. And then we talked about the Fibonacci game last time, so I hope everybody watched the lecture. And we moved to a new decomposition by moving in the following way. If we have a summand that's repeated, if we have two FKs, we can write that as FK plus 1 plus FK minus 2. We have to be a little bit careful because if it's two F2s, then it becomes an F3 plus an F1. And if we have two adjacent terms, an FK and an FK plus 1, we can remove that with an FK plus 2. Okay? So those are the two moves we're going to have in our Zeckendorf game. Now what we want to do is we want to see what do these legal moves do to a decomposition. In particular, what do they do to the index of the decomposition? So the claim is that the index is a monovariant, that as you apply either of these moves, it cannot increase the value of the index, it can only decrease it. So the first thing we do is let's look at what happens if we use the doubling. 2FK is equal to FK plus 1 plus FK minus 2. So let's see what the contribution is to the index. Well, we said the index is defined by taking, if you have the term FK, you multiply the number of copies of it by K. So 2FK, does everybody agree that it's going to contribute 2K to the index? So I need a yes or a no.
I think yeah.
Does everyone agree that 2FK is going to contribute 2K to the index?
Yeah.
Yes.
All right, that's 2 yeses. Somebody hasn't spoken, I think. I think we have 3 people today. Does everyone agree? I'm missing 1 yes. All right, let's do it one more time. Everybody go one at a time. Say your name and say yes or no.
I'm Li. And I think yes.
Okay, that's 1 yes.
Dongxia. Yes.
That's 2 yeses. Do we have 3 people today or only 2 people on?
3.
Who has not spoken? Am I missing something? Did we have 3 people speak or just 2 people speak?
We just have 2.
Okay, who did not speak?
I think it's Yi.
All right, for the person who did not speak, do you agree that 2FK contributes 2K to the index? I know sometimes the net connection is bad and it's tough to hear people. So for the person who did not speak, do you agree? I need you to say yes or no right now. I know this is frustrating, but I want to make sure everybody understands. So let's do it one more time. I can't see who's online because I've got my screen on full. Do we have 3 people online today?
Yes.
Can someone tell me if there's 3 people online?
Yeah.
Yeah.
So I'm only hearing 2 people right now. Is there a 3rd person online? Everybody, please say your name right now. Just say your name, one at a time.
I'm 若慈.
That's 1. That's 2. Did we just have 2 people speak or 3 people speak?
2 people speak.
Is there somebody who is not speaking?
I think all of us speaking.
Are they able to speak right now?
Yeah.
So do we need to do it again?
Let's do it again.
Okay. I'm Zhi.
Say your name. That's 1. Okay. Next person.
I'm 若慈.
That's 2. We need 1 more person. Okay, that's it. We've got 3 people now. Excellent. Now we're going to go in the same order and say yes or no. Do you understand that 2FK contributes 2K to the index? Say your name and say yes or no.
Yes. Zhi say.
That's 1 yes.
Yes.
That's 2 yeses. Say your name. Okay.
I'm 若慈 and yeah.
Okay, that was 2 yeses. And now the 3rd one.
There's 3 already.
Okay, we already got 3 yeses?
Yeah.
Okay. Again, it's sometimes hard to hear with the connections. I really want to make sure that we all understand this because after this lecture, the goal is to have you starting to do research. So everybody agrees that 2FK contributes 2K to the index. What does FK plus 1 contribute to the index? So what, can somebody tell me what FK plus 1 contributes to the index? If we have 1 copy of FK plus 1, what does that contribute?
We got 1 FK.
Right, so what does 1 FK contribute to the index?
$1K.
So what does what does F8 contribute to the index?
$8.
It contributes 8. What does F13 contribute to the index?
13.
13. So what does FK plus 1 contribute to the index?
K plus 1.
Yeah.
Yes, K plus 1, exactly, excellent. What does K minus 2 contribute to the index?
K minus 2.
Good, so Fk plus 1 plus Fk minus 2 contributes K plus 1 plus K minus 2, which is going to just be 2K minus 1. So notice the index went down. Okay, does everyone agree that the index went down if we go from 2Fk to Fk plus 1 plus Fk minus 2?
Yes.
Yeah.
Now, if we had, what we had above, if we had 2F2 goes to F3 plus F1, then you get 2 times 2 is 4, 3 plus 1 is 4, so there's no change in that case. But in every other case, the index went down. The other move we could do is we could combine Fk plus Fk plus 1 and get Fk plus 2. the left-hand side is going to contribute 2k plus 1. The right-hand side is going to contribute k plus 2. Is 2k plus 1, is that ever larger than k plus 2? So do you think 2k plus 1 is larger, or do you think k plus 2 is larger?
K plus 2 is large.
Yeah, what's the only time that they're going to be the same?
Just -1.
Well, remember, the smallest k can be is 1.
K equals to 1.
Yeah, when k equals 1, they're going to be the same, because both sides will be 3. But other than that, it will go down. So what we see is that whenever we apply any of these moves, the value of the index cannot go up. It has to stay the same or get smaller. Okay?
Okay.
And then what you need to do is you need to then show that as you keep playing, as you keep doing these moves, you eventually end up in the Zeckendorf decomposition. I have written this up nicely with my students. You are welcome to just read that paper. You are also welcome to try to prove it yourself and see if you can. It will, it's a hard problem at times. You learn more by trying things. And the idea is if we're in the Zeckendorf decomposition, can we apply one of these two moves? Would we have something that's doubled if we're in the Zeckendorf decomposition? So if we're in a Zeckendorf decomposition, would we ever have something like a 2FK or a 3FK or 4FK in our decomposition? So what did we say earlier about the values of the B's in a Zeckendorf decomposition?
Is 1 or 0.
They're either 1 or 0. And if you have a 1, the term before and the term after have to be 0. So is it possible in the Zeckendorf decomposition to have a 2FK or a 3FK or a 4FK?
No.
No. So we know if we're in the Zeckendorf decomposition, we can't use the rule replace twice FK with FK plus 1 plus FK minus 2. We can't use that. What about the other move? Take two adjacent numbers, FK and FK plus 1, and replace it with FK plus 2. Can we do that if we're in the Zeckendorf state? Would we have
Yes.
we could combine?
Yes, I think.
So that would mean in a Zeckendorf decomposition, we would have maybe like an F7 and an F8 next to each other. We would have two adjacent summons. That's
Right.
why we need to use this rule. Can we have two adjacent summons in a Zeckendorf decomposition?
No.
No. So what this tells us is that if we happen to hit a Zeckendorf decomposition, we can't do any more moves. The process stops. So if these are the two moves we do, once we hit a Zeckendorf decomposition, we're done. What you need to show is that if you're not at the Zeckendorf decomposition, well, then that means you can always do one of these moves. And you need to just show that eventually you hit the Zeckendorf decomposition. And since the monovariant is always going down or staying the same, the Zeckendorf decomposition has to have the smallest value. That's not quite the same as showing it has the smallest number of summons.
Okay.
Right. Clicker's not working. Okay. So now let me go through the Zeckendorf game again, because this is what I really want you guys to analyze. So it's a two-player game. You take turns. The last person to move wins. So we have the bins that are the Fibonacci numbers, F1, F2, F3, F4, F5. So 1, 2, 3, 5, 8, 13. And we start off with n pieces in bin F1, and all other bins are empty. And then on your turn, you can do one of the following two moves. If you have two pieces in a bin, you can remove them and put one piece at Fk plus 1 and one piece at Fk minus 2. And then if we had two on F1, we have to be a little bit careful. That becomes one piece on F2. And then the next one is if we have pieces on bins Fk and Fk plus 1, we can remove those and put one piece at Fk plus 2. And so there's a couple of questions you can ask about the game. Does the game end? If so, how long does it take? For each n, who has a winning strategy? Because it's a, if it's a finite game, one of the players is going to have to win. And then the next one is, can you determine a winning strategy? What my thesis student and I proved a little bit over a year ago is that as long as n doesn't equal 2, player 2 always has the winning strategy, but it's a non-constructive proof. It means we prove the existence of the strategy, but we don't know what it is. So if you could figure out what the winning strategy is, that would be a tremendous advance. We actually presented this at the 18th International Fibonacci Conference, and the audience was very interested in this. So this is a problem that has already been presented at a conference that a lot of people found very interesting. So if you can prove things about this, there will definitely be a receptive audience. I'm one of the organizers of the next International Fibonacci Conference, which will be July 2020 at the University of Sarajevo. And so if we are able to get good results, there's the possibility of actually going and presenting at the World Fibonacci Conference. So let's imagine a simple game. Let's say we start off with 10, so big N equals 10, and we put all of the pieces on F1. So I've got the little game board here. And now I start to apply my moves. There's really only one move I can do because the only thing I have is I have 10 pieces on the Fibonacci 1. So I have to take 2 of them and make it into a 2. Does everyone agree that that's my only move because I don't have any 2 adjacent pieces?
Yes.
Yeah.
Okay, so I have to do F1 plus F1 is F2. So now notice I have 8 pieces in F1, 1 piece in F2, and notice 8 times 1 plus 1 times 2 is still equal to 10. Now I have 2 possible moves. I'm going to have player 2 take 2 pieces in F1 and make a new piece in F2. What else could I have done? What other move could I have done?
Combine one from F1 and one from F2 into F3.
Excellent. I didn't do that though, so I have 6 in F1 and 2 in F2. Now it's player 1's turn, and I'm going to have him take the 2 pieces in F2 and split and make 1 in F3 and 1 in F1. What else could I have done?
We can make 2 F3.
I'm sorry?
We can make 2 F3.
How can I make 2 F3?
We can have 2 F2 and 2 F1 into 2 F3.
No, you can't do that. You can't do that. That's not a legal move. A legal move is you can take something that's doubled and, or you can take 2 adjacent things and combine. But what you could do is you could take something in F1 and something in F2 and make something in F3. You just can't do it twice. That would count as 2
Okay, so we can do 1.
Right, so you could do F1 plus F2 is F3. What else could we have done?
We can make another F2.
Perfect. So those are all the moves possible. I'm going to take the F2 and split it. So now we have 7 in F1 and 1 in F3. The only move now is to take 2 F1s and make an F2. So now we have 5 F1s, 1 F2, and 1 F3. And notice that 5 times 1 plus 1 times 2 plus 1 times 3 is still 10. So I'm going to say now my player 1 is going to have F2 plus F3 gives us F4. What else could we have done?
We can make another F2.
Good, we could have made another F2 by taking 2 F1s and making an F2. And there's one more move.
Or make another F3.
Excellent. So you guys are getting the hang of the game very quickly. Now, when I'm in this situation, the only move I have is to take 2 F1s and make an F2. Now, I'm going to say player 1 is going to take an F1 and an F1 and make an F2. What else could I have done?
Make an F3.
Excellent. So now, player 2, I'm going to have take an F1 and an F2 and make an F3. What else could player 1 have done? Could player 2 have done?
We can have 1 F1 and 1 F3.
Right, they could have split the doubled at F2. And now on this point, I'm going to have player 1 takes F3 and F4 and make an F5. What else could player 1 have done?
We can make a F4.
Excellent. And now at this point, there's no moves left and player 1 wins. Now I told you that we actually have as a theorem that player 1 will always lose if n does not equal 2 if player 2 plays intelligently. So this means a mistake was made somewhere. So here's the list of the moves of our game. And if you notice, there's a blank row. And the reason I have the blank row is, we start off, it's player 1's turn, player 1 moves, and then we come here, it's player 2 turns, player 1's turn, 2's turn, 1's turn, 2's turn, 1's turn, 2's turn. And we had player 2 move to here. So player 2 took an F1 and an F2 and made an F3. What else could they have done?
They can have 1 more F1 and 1 F3.
Good, so we could have had this move. And notice if we're in this position now, if player 1 takes the 2 1s and moves back to F2, we were basically back to where we are, but 1 move later. So we're at the same game state, but we change whose turn it is. And this is called a parity switch. And we talked about the game of Chomp, where you can prove there is a winning strategy, and what happens is player 2 needs to switch with player 1. So here's a couple of results. All games end in a finite number of moves. Instead of using the monovariant, where the index is basically the weighted sum, it's much better to use a slightly different one where you take the square root of the index rather than the index. And if you do that, then you get that it's, I believe, strictly decreasing. And so the game will have to end. It'll be a little bit easier to prove. So again, it's hard to do math live when you have a professor lecturing to you. You often need to just stay by yourself, look at it for a while. So I'm not going to go through all the details here. I will send the paper for you to look at. But it turns out that it's a little bit easier if we use this as the monovariant. We actually have an upper bound for the number of games. It's the logarithm, and the base is the golden mean. the fastest game, we actually have some results about what the fastest game is. If you look at a plot of random games, it actually looks like it's becoming a Gaussian. This would be a wonderful thing to try to prove, but if you don't know calculus, it's going to be very hard. Even if you do know calculus, there's a lot of other things we would have to introduce. If you can do some numerical simulations, it would be wonderful to provide more evidence for this. So out of curiosity, is there anybody here who is good at coding? Okay, so we might bring in one of my undergrads, some of the coding for stuff like this. So I'm going to talk a little bit about why player 2 has a winning strategy. I'm not going to give the full proof, but I want to give you a flavor. So we talked about the game Chomp, where whoever goes last loses. And if you choose a square or a circle, you eat everything from that circle up and to the right. And so I'm going to prove to you that player 1 has a winning strategy. So there's two cases for given board. Player 1 has the winning strategy, or player 2 has the winning strategy. If player 1 has the winning strategy, then we're in great shape because we're trying to prove player 1 has the winning strategy. Assume now that we have a board where player 2 has a winning strategy. So let's have player 1 take the upper right circle. We are assuming player 2 has a winning strategy, so there's some place they can go which will put them on the path to win. Let's say it was here. And now player 1 can say, wait a minute, I didn't mean to go here. Now that player 2 knows that if they go over here, and it's player 1's turn from this point onward, player 1 knows that they're going to lose. So player 1 changes his mind, and player 2 goes where player 2 wanted to go on their first turn. And what happens is we come to the same board state, but we come to it one turn earlier. And so we change the parity of who's going next. So what's wonderful about this is it proves that player 1 has the winning strategy. What's annoying is it doesn't tell us what that strategy is. So I'm going to try to quickly show you the proof that player 2 has the winning strategy as long as n is not equal to 2. So what I have here is a tree to try to show you what the various game states are. And so you see numbers like 1, 2, 3, 5. These are the Fibonacci numbers. And the exponent is going to be how many copies of them we have. Okay?
Yeah.
So 1 to the n means we basically start the game with n copies of 1. There's only one possible opening move, right? We have to take two things from 1 and make it go into a 2. So does everyone agree that this is the only possible first move to go from here to here?
No.
And then we have two possibilities. We could take 2 more 1s and make another 2, which would bring us to over here. And now we would have n minus 4 1s. Or we could take a 1 and a 2 and make a 3. And so if we have a 1 and a 2 and we make a 3, then we only have one possibility for the next move. We have to take 2 1s again and make a 2. If we were over here, we would have 2 possible moves, and so on and so on. So the problem is the number of paths grows very rapidly. What I want to do now is I want to show you that if we assume that player 1 has a winning strategy and n is at least 3, then we have a contradiction. So what I'm going to do is I'm going to color a square. What color does that look to you?
Red.
Colors are often changing when they get projected onto different computers. What color do you see it as?
Red.
Okay. It's supposed to be red. It's looking a little bit more orangey on my computer today, but let's call it red. So I'll call it red if player 1 has the winning strategy and blue if player 2 has the winning strategy. So we start off, and by assumption, we're assuming player 1 has the winning strategy, and we're going to get a contradiction. So we only have one possible move. So when we come to this cell, what color is that cell going to be? Is it going to be red or blue?
Blue.
Why blue?
Blue, I think.
I'm sorry?
Blue.
No, it's still going to be red because player one has the winning strategy. Player one's only move is to go here, right?
Yeah.
So if we're at this place, it's still got to be a winning strategy for player one. So this is extremely important. We could actually make the graph even more complicated and keep track of whose turn it is when we're at a given cell. But at that point, if we're in that cell, player one is going to have the winning strategy.
I have a question.
Yes.
So like for n is that the least numbers of the moves that can for player one to win?
Say it again, is n the least number?
Least number of moves for player one to win?
No. Right now we're assuming that we start off with n numbers on one. We start off with the number, say maybe 2019 or 75.
So what does that mean?
Well, just when we were playing our game earlier, it says we start off with 10 pieces at F1 and the rest is empty. So in this case, n would be 10.
Oh, okay.
Oops. So do we all agree that if we're assuming player one has the winning strategy, when we go here, player one still has to have the winning strategy?
Yes.
Now, player two has two possible moves. Could either of those moves lead to a player two victory?
No.
No, we're assuming player one has a winning strategy. So both of those moves have to be winning strategies for player one. Now things get a little bit more interesting. Over here, there are two possible moves for player one. Is it possible that one of those moves is bad?
Yes.
Yes, so we don't know what color those two boxes are. It's possible both of them are still pink, but maybe one of them is now blue. One of them could be a mistake for player one. What about this box over here? Does that have to be a win for player one?
Yeah.
Yes, because if we're over here, can people see my mouse when I do this?
Yeah.
Okay, if we're over here and player two has just moved, when we are here, we only have one possible move that has to go there for player one. So now once we're here, that has three possible moves for player two. By assumption, what can you tell me about all of those moves? So it's player two's turn. Player two can either go here, here, or here. What must be true about all three of those? Who must win for each of those?
Player one.
Wait, we're assuming player one always has the winning strategy. So when we're over here, no matter where player two goes, player one has to be able to win. So we come to all three of those, and player one has to win. Okay. Now it's player one's turn again, right?
Yeah.
Now, things are getting more complicated. And we start to look at where could player one go. And you can see there's a lot of things down here player one can go. Let's focus on this square over here. Player one could go over here, okay? And I claim that that should be colored blue. Why should that be colored blue? So let's go through things very carefully. Here is player one's turn, player two's turn, player one's turn, player two's turn, player one's turn, and then player two's turn, okay? So over here, we're assuming that when we're at this board configuration and player one is going, player one has the winning strategy. If we come to here, whose turn is it?
Player two.
Player two. And we just said, if we were in this state and player one is going, player one has the winning strategy. So that means if we're in this state and player two is going, player two has the winning strategy. Right?
Right.
Because it's the same configuration as this one, but we've just changed whose turn it is. And we just said, whoever's turn it is here, it's player one's turn, they have the winning strategy. So that means if player two can get to here, they win.
Oh, yeah.
So that means if they get to this square, player one,
Yeah.
so it just propagates, upwards. So I'm not going to go through the rest of the details. You know, I will let you look at the paper, but that's essentially what's going on, is that we find out that there's two different ways to get to the same board configuration, and player two can do a parity switch. So what I want to do is I want to give you guys an original research problem that no one has looked at. So I've listed some kind of future work. You know, one is what happens if you have more people playing? And we've done a little bit of work on that. That's something you can definitely look at. And is what happens if you move randomly? But I'm afraid it requires too much calculus and advanced mathematics. And then another thing is you could look at other sequences. And so I had some students this summer looking at a generalization of this on the Fibonacci quilt sequence. But what I want to do is I want to give you a very specific problem to look at. And the problem I want to give you is, let's go back a little bit to how things were defined. So for a turn, we have two possibilities. We can either take something that's doubled and split it, or we can take two adjacent things and combine it. Okay?
Okay.
What I want to do now is I want to play a deterministic game. Have you ever played the card game War? What you do is you split the deck into two, and you and your friend go 1, 2, 3, War, and you turn over a card, and whoever's card is highest wins. Have you ever heard of this game?
Nope.
Okay. It's a very easy game to describe. I've basically just given all the rules. There's something you do if two cards are the same. It's called a tie. You then the simple version is you then just turn over the next card. And you keep doing this until somebody has a higher card than the other. And if two cards are the same number, you say spades is higher than hearts, is higher than diamonds, is higher than clubs. There's no strategy in this game. It's completely deterministic. Have you ever seen the game Candyland? You have a board with squares of different colors, and you pick a card from a pile, and if it has a yellow, you move to the next yellow square.
No.
There's no strategy.
No.
All right, another game is Chutes and Ladders. You ever seen Chutes and Ladders? This is unfortunate. We have different toys as we grow up. So there's a couple of games for very young kids where there is no strategy. Everything is completely determined. But the little kids don't really understand that, and they still think it's fun to play. So the question is, what if we made the Zeckendorf game deterministic? So right now, on your turn, you have two possible moves. If you have a double, you can split it. If you have two adjacent pieces, you can combine it. What I want you to do is I want you to analyze things, but now I'm going to give you another rule. I'm going to tell you, if you have a choice of multiple moves, which move you have to do first. Consider the suggestion of which move you have to do first. So we have two moves, correct?
Yes.
Can somebody give me a suggestion of a move that we should do first? But if we have a choice, what move should we do? You might be hesitant to say something because you might think the problem is too simple. This is really a simple question. We have two moves. Give me a suggestion. If we have the possibility of doing both, which should we do first?
Remove and add one.
Okay, so say it again. What should we do?
Remove and add one. So the second.
I can't. Okay, what should we do? Okay, remove and add one. So we should do, if we have something at fk and fk plus 1, do that before splitting a double. Excellent. What's the other possibility?
We can also split.
Right, so there's two possibilities. One possibility is when we're trying to make the game deterministic. If you have a choice, if you can do both types of moves, always do the remove and add one before you do any splitting move. The other possibility is if you have a choice of doing either, always split a double before you remove and add one. This is not quite enough to make the game deterministic. What if we have several different remove and adds? Which one should you do first?
From the biggest one.
Good. What else could you do first?
The smallest one.
Smallest. So you see that there's two possibilities. There's two very clean ones. Always do remove and add, and do the largest remove and add that you can. Always do remove and add first, and do the smallest remove and add you can. And then similarly, always do the split the double, and split the largest double first, or always do the split the double first, and do the smallest double. So that's 4 different deterministic games to analyze. Okay? Is there any strategy anymore in these games? Is there any strategy anymore? So strategy means that you have a choice in what you can do and you can try to play well. Is there any strategy in these deterministic games?
No.
No. Is your move completely determined by the rules?
Yes.
Yes. So my question to you is, here are 4 different deterministic games. Sadly, there's only 3 of you. Who wins for different values of n? When n equals 1, 2, 3, 4, 5, 6, 7, can you tell me who wins?
Yes.
It would be great if you had the ability to write a computer program. But for small values, I think you can do these by hand, and you can start assembling a table. And the question is, can you figure out, is there a nice pattern as to who's going to win each game? Depending on which of the 4 ones you're looking at. So is it clear what the goal is and what the question is?
Yes.
So again, the object was to try to find a research question the math community would be interested in that you can handle without calculus and with just the high school math that you know. And so I think this problem is going to be accessible. We can at least describe it, and so you can get a sense of what it is. And so now what I'm going to do is one of you or maybe all of you together should write a little summary and explicitly state what the research question is, and then we'll assign 3 of the games to 3 of you, and then we'll save on the 4th one for a while. And then we'll start gathering some data and start trying to get a sense of, can we tell who's going to win? And then depending on how things go, we might try to analyze other related games. and see if we can find some kind of pattern. So I want you to think and get back to me within a day. Does this sound like an interesting project? Does this sound like a project you think you can make progress on? Okay?
Okay.
Okay.
So, again, the further you go in life, the more math you're going to know, and the more is going to be available to you. So, right now, we don't have nearly as much as we would have in 4 years after you've taken a lot more classes. That's fine. There's still a lot of great, interesting things to investigate. It just means we're a little bit limited in terms of what tools we have at our disposal. And that does affect a little bit what problems we might want to study. So if you could program, you could do this a lot faster. And we might talk a little bit about how to write programs, depending on what your backgrounds are. But you can at least do a bunch of these by hand, and maybe you can start detecting a pattern and trying to figure out who might win for various values of n. All right, have a great evening, and I will send you a summary email later tonight.
Okay. Good night.
All right, good night.